When an apple snaps from a branch and drops to the grass below, it feels ordinary. We know exactly what to expect. In the late 1600s, Isaac Newton looked at everyday falling objects and realized there was a hidden mathematical relationship at play. He determined that anything with mass naturally pulls on everything else with mass. He published a strict mathematical rule for this attraction in 1687. With Newton's equations, anyone could calculate exactly how fast an object would fall or how strongly a planet would pull on its moon. But there was a persistent catch. Newton could run the numbers perfectly, but he could not explain how this force actually traveled across empty space. How does a massive planet reach out and grab a distant object? He gave us the reliable math to predict exactly what gravity does, but the actual cause of the pull remained an invisible, almost magical mystery. That mystery persisted until 1915, when Albert Einstein threw out the idea of an invisible pulling force altogether. Einstein proposed our universe is built on space-time, a continuous fabric stretching in all directions. A heavy star pushes down, actively curving the grid. A smaller object traveling nearby isn't pulled by an invisible magnet. It simply rolls along the natural downward dip. Einstein realized that inside a closed box jerked upward through deep space, you would feel pressed against the floor exactly as if standing on the ground. He concluded that acceleration and gravity feel identical because they are the same physical effect. Einstein's insight redefined gravity as the physical shape of the universe itself, a geometry that bends and shifts whenever mass or energy is present. To see if this fabric concept holds up, we have to look beyond our solar system and observe the most intense environments in deep space. The ultimate stress test is a supermassive black hole. These objects pack in so much matter that they warp the fabric into an infinitely deep sinkhole, a curve so steep that not even a particle of light has the energy to climb out. Recently, scientists linked up a massive network of radio telescopes across the globe to look directly at the center of a galaxy and capture an image of one of these light-trapping sinkholes. What they captured was the shadow of a black hole in the galaxy M87. When they measured the size and shape of that shadow, it was an exact match for the math Einstein wrote out over a century ago. Even under the most brutal, highly warped conditions imaginable, this geometric model passes the test flawlessly. We can zoom out even further to view galaxy clusters. These massive collections of stars and gas are the absolute largest structures governed by gravity in the universe. But when astronomers study these massive clusters, they notice a major anomaly. The outer edges of these galaxies are spinning far too fast for the amount of visible matter they contain. Based on what we can see, they should be tearing themselves apart and flying off into deep space. Because we know Einstein's rules of curved space work perfectly even in extreme conditions, the math tells us that something else must be weighing down the fabric to create the extra gravity holding the galaxy together. Physicists call this hidden source dark matter. We cannot see it directly, but it adds massive amounts of unseen weight, creating deep curves in spacetime that keep those fast-moving stars safely in their orbits. By relying on gravity's predictable geometry at a massive scale, we can map out the invisible materials that literally hold the cosmos together. But watch what happens when we reverse direction. If we leave the massive galaxies behind and zoom all the way down to the microscopic scale, the rules break down. Welcome to quantum mechanics. This is the branch of physics that governs the behavior of incredibly tiny things, like atoms and subatomic particles. Einstein's gravity relies on a smooth fabric, but the quantum world isn't smooth. It's made of discrete chunks, behaving randomly. At this scale, physicists find quantum foam. Space and time boil so violently that a measurable curve loses all meaning. When scientists try to write an equation that combines the smooth, predictable slopes of gravity with the chaotic, jumping particles of the quantum world, the math stops working entirely. Our two best descriptions of reality describe two different universes that refuse to fit together. It means our map of how things work has a massive gap right where we need it most. Right now, researchers are racing to fix this crack in physics. To bridge the gap, they are trying to prove that gravity actually has a chunky quantum nature of its own. They are hunting for a theoretical, undiscovered particle called a graviton. If it exists, this tiny physical messenger would be responsible for carrying the force of gravity from one place to another. Finding one is incredibly difficult. Gravity is trillions of times weaker than the other forces in nature, meaning that isolating a single graviton requires precision far beyond what our current machines can see. What began as a question about a falling apple has led us to the most difficult hunt in history. Finding that tiny particle is the final connection we need to weave our separate theories of the large and the small into a single,